Steel should not float in the sky, yet every single day it does, and not in small pieces but in giant machines that weigh as much as a Navy destroyer, stretching longer than a football field, carrying hundreds of people, thousands of meters above the ground, and moving at speeds faster than most bullets from the early 20th century. And the strange truth is that airplanes should not be able to fly, at least not in the simple way most of us were taught in school, because when you look at a modern jetliner, a 200-ton machine made of metal, fuel, seats, engines, and cargo, it feels wrong that it can rise into the air and stay there for hours, crossing oceans and continents, as if gravity has been quietly switched off. Yet gravity is still there, pulling down with the same force it has always had. And even scientists once argued fiercely about how this actually works, not about whether planes fly, because they clearly do, but about why the air lifts them the way it does. And here is the part that most people never hear. Even today, experts debate the clean, simple explanation that appears in textbooks, because the real answer is deeper, more complex, and more fascinating than a single classroom diagram of a curved wing and two arrows showing fast air on top and slow air below. In this video, you are going to learn why the common explanation of flight is incomplete, how early aviation pioneers like the Wright brothers built flying machines before the physics was fully understood, how the famous Bernoulli principle became the popular story of lift, and why that story does not fully explain how fighter jets can fly upside down, or how paper airplanes with flat wings can stay in the air. You will discover how Isaac Newton's third law plays an equally powerful role, how wings push air downward to push themselves upward, and why the real answer lives inside a branch of physics called fluid dynamics, one of the most difficult areas of science, where equations stretch for pages and tiny changes in airflow can change everything. You will also learn how major aerospace companies like Boeing and Airbus do not rely on one simple formula, but instead use massive computer simulations and wind tunnel testing to model millions of case airflow patterns, because air is not calm and smooth like it looks from the ground. It is chaotic, swirling, forming invisible tornadoes called vortices at the tips of wings, bending around surfaces in ways that are almost impossible to predict perfectly. And this hidden chaos is part of the reason the debate about lift has lasted for more than a century. There were moments in history when respected scientists openly disagreed in journals and conferences about which explanation should be taught to students, and even organizations like NASA publish multiple descriptions of lift, not because no one understands flight, but because reducing it to one sentence removes the truth that several forces act together at the same time: pressure differences, downward deflection of air, momentum change, circulation around the wing, and complex boundary layers that cling to metal surfaces as the plane races forward. By the end of this video, you will see that airplanes do not fly because of one magical law. They fly because physics is layered, because air behaves both simply and wildly at the same time, and because engineers learned to work with nature long before every equation was fully solved. And that realization changes how you look at the sky, because what once seemed like a basic engineering trick becomes a masterpiece of controlled forces balancing perfectly against gravity. Stay with me until the end, because the final piece of this puzzle explains why saying nobody really knows why airplanes fly is both wrong and strangely close to the truth. And once you understand that balance between knowledge and mystery, every takeoff will feel different, every wing will look more powerful, and the sky will seem less empty and more alive with invisible motion, shaping every flight. Welcome to our channel, where we break down complex ideas into clear and powerful stories. And if you enjoy discovering the deeper side of science and technology, make sure you subscribe and join us for the next journey into the hidden forces that shape our world. Aluminum, titanium, steel, wires, fuel, seats, engines, screens, cargo, and people are packed into a single machine that can weigh more than 200 tons, and that machine rolls slowly down a runway before rising into the air as if it has quietly ignored gravity. and when you stand close to a modern airliner, the scale feels overwhelming, because the wings stretch wider than many buildings are long, the engines are taller than a person, and the body of the aircraft is like a metal tunnel designed to cross oceans without stopping, and yet this massive structure lifts off the ground with a smooth motion that almost looks gentle, even though nothing about it is small or light, and when fully loaded, some long-range jets weigh as much as a naval warship or a fully loaded freight train, solid, heavy, dense machines that belong on water or on rails, not in the sky, and still they climb higher and higher until they are cruising above the clouds where the air is thin and cold, and the feeling that this should not be possible never fully goes away, because our everyday experience tells us that heavy objects fall, rocks fall, cars stay on roads, buildings stay fixed to the ground, and metal sinks in water. So watching a giant metal aircraft float in air feels like watching a mountain drift upward. And this tension between what feels natural and what physics allows is where the real story begins, because if something that heavy can leave the ground and stay up for 10 hours, then the forces involved must be powerful, precise, and deeply connected to the invisible behavior of air itself. And that leads to the simple but powerful question that sits at the center of flight. So how does something this heavy leave the ground? The first real breakthrough did not come from a perfect theory or a complete set of equations. It came from two bicycle mechanics in the early 20th century who were willing to test ideas again and again until something worked. And the Wright brothers did not begin with a full understanding of fluid dynamics or advanced mathematics. They began with curiosity, observation, and careful experimentation. And at the time, many respected scientists believed powered flight would remain impossible because earlier attempts had failed in dramatic ways. Gliders crashed, engines were too weak, wings were poorly shaped, and control systems were unstable. Yet the Wright brothers approached the problem step by step, first studying how birds moved their wings, then building small gliders to test balance and control. And when they realized that existing data about lift was unreliable, they built their own wind tunnel, a simple wooden box with a fan that allowed them to measure how different wing shapes behaved in moving air. And this was a turning point, because instead of trusting assumptions, they gathered their own data, adjusting the curve of the wing, changing angles, testing again, measuring again, learning from each small failure. And through trial and error they discovered that control mattered as much as lift, that twisting the wings slightly could stabilize the aircraft, and that a powered engine combined with efficient propellers could provide enough thrust to sustain flight. And in 1903, their flyer lifted off the ground for a short but historic flight, proving that controlled powered flight was possible. But even then, the deep physics of why the wings generated lift in the exact way they did was not fully understood, because discovering that something works is not the same as fully understanding why it works at every level, and that difference would shape the next century of aviation science, because building a flying machine through testing and observation solved the practical problem, but explaining flight in a single clear theory would prove far more complex, and discovering something is not the same as fully understanding it. As aviation grew and aircraft became more common, scientists looked for a simple explanation that could be taught in classrooms and printed in textbooks, and one name often connected to this explanation is Daniel Bernoulli, an 18th-century mathematician who studied how fluids behave. And Bernoulli's principle describes how the pressure of a fluid changes as its speed changes, and the common story presented to students is clean and easy to follow. A wing is shaped with a curved top and a flatter bottom. When air moves over the wing, the air traveling across the curved top has to move faster than the air below, and according to Bernoulli's principle, faster moving air has lower pressure. So the pressure on top of the wing becomes lower than the pressure below, and this pressure difference pushes the wing upward, creating lift. And this explanation feels satisfying because it connects shape to speed and speed to pressure, forming a clear chain of cause and effect. And diagrams often show two air particles separating at the front of the wing and meeting again at the back, with the top particle moving faster to catch up, and the result appears logical and simple. Faster air on top, lower pressure, upward lift, and for many years this became the standard explanation of why airplanes fly, printed in textbooks, shown in classrooms, repeated in documentaries, but this explanation is incomplete. The problem begins when we look at real aircraft that do not fit the simple picture, because many wings are not strongly curved, some are almost flat, and yet they still generate lift, and fighter jets can fly upside down for short periods, which seems to break the idea that a curved top is required to create lower pressure above the wing, and aerobatic planes can perform loops and rolls while maintaining lift in unusual orientations, which means the shape alone cannot explain everything. And if two air particles do not actually meet again at the back of the wing at the same time, as more accurate experiments show, then the simple equal transit explanation taught in many classrooms does not hold, and engineers who design wings often describe lift using pressure distribution graphs rather than simple stories about curved surfaces, and physicists point out that Bernoulli's principle is valid, but does not by itself explain why the air speeds up over the top of the wing in the first place, because something must cause that acceleration, and that deeper cause involves the way air is deflected and how circulation forms around the wing. And when experts discuss lift in professional settings, the conversation quickly moves beyond the basic textbook diagram into more detailed analysis involving momentum change and boundary layers. And this does not mean the textbook explanation is completely wrong. It means it leaves out important physics. It simplifies a complex interaction into one clean idea. And while that simplicity is useful for beginners, it can create the false belief that flight depends only on wing curvature and pressure difference in a narrow sense, when in reality the situation is more dynamic and more connected to how air is pushed and redirected. So what is really happening? Another powerful piece of the puzzle comes from Isaac Newton's third law of motion, which states that for every action there is an equal and opposite reaction, and when applied to flight, this law suggests a straightforward idea. If a wing pushes air downward, then the air must push the wing upward with equal force, and when a plane moves forward, its wings are angled slightly so that they deflect incoming air downward, and this downward change in momentum means the air leaves the wing moving toward the ground, and in response the wing experiences an upward reaction force, which we call lift, and this explanation focuses less on pressure differences and more on the direct movement of air mass, emphasizing that lift comes from redirecting airflow, and it helps explain why planes need speed, because without forward motion there is no steady stream of air to deflect. And it explains why airflow is essential, because lift depends on interacting with a large volume of air every second, and when engines provide thrust, the plane accelerates, increasing the rate at which air is pushed downward, increasing the upward reaction force. And both Bernoulli's principle and Newton's third law describe aspects of the same physical event from different angles. Pressure differences are connected to changes in momentum, and momentum change is connected to pressure forces acting on the wing surface, and separating them completely can be misleading because they are two ways of describing a single complex flow pattern. And even this combined view remains simplified compared to the full mathematical treatment used in advanced fluid dynamics, where equations describe how velocity fields, pressure gradients, and viscosity interact in three-dimensional space around a moving wing. The reason experts sometimes appear to disagree is not because the fundamentals are unknown, but because the language used to explain them depends on the level of detail and the audience. Organizations like NASA provide multiple explanations of lift, tailored for students, teachers, and engineers often focus on pressure distribution maps measured in wind tunnels, showing exactly where high and low pressures form across a wing surface, while physicists may focus on solving the Navier-Stokes equations that govern fluid motion, equations so complex that no general solution exists for all cases, and fluid dynamics as a field is known for its difficulty because air is not a simple smooth substance. It behaves in ways that can shift from orderly flow to chaotic turbulence within small changes of speed or angle. And as air moves over a wing, it forms thin layers that stick to the surface due to viscosity, called boundary layers, and these layers can remain smooth for a time before separating and creating turbulent wake patterns behind the wing, and at the tips of wings swirling vortices form as high-pressure air from below curls upward to meet lower-pressure air above, creating spinning tubes of air that trail behind aircraft and can affect other planes. And all of this happens invisibly at high speed, shaped by temperature, air density, humidity, and precise wing geometry. And modeling this behavior requires advanced computer simulations that divide the air around a wing into millions of tiny cells, calculating pressure and velocity at each point. And even then, approximations are necessary, because solving the full equations exactly for every condition is beyond current computational limits. And this is why explanations vary. Some focus on momentum, some on pressure, some on circulation theory, developed in the early 20th century, and each highlights a different aspect of the same reality. So the truth is not magic, it is complexity. In modern aviation design, companies like Boeing and Airbus approach lift not as a single formula, but as a design challenge shaped by data, simulation, and testing. And engineers use powerful supercomputers to simulate airflow around new wing designs under many conditions, adjusting curvature, thickness, sweep angle, and winglets to optimize performance, fuel efficiency, and stability. And these simulations can model millions of airflow patterns, predicting how small changes will affect drag and lift at different speeds and altitudes. And after digital modeling comes wind tunnel testing, where scale models are placed in controlled airstreams to measure real pressure differences and force distributions, and sensors record how air behaves at various angles of attack, revealing where flow remains attached and where it begins to separate. And even after years of experience, designers do not rely on a single principle, but on an integrated understanding built from theory, computation, and experiment. And while the sky is predictable enough for safe and routine flight across the globe, the underlying airflow patterns are too rich and detailed to be captured by a short explanation, because lift emerges from the interaction of pressure fields, momentum transfer, circulation around the wing, and the continuous deflection of air downward. And when a plane cruises at high altitude, its wings are carefully shaped to operate efficiently in thinner air, balancing weight, thrust, drag, and lift in a delicate equilibrium that must hold steady for hours. The big realization is that airplanes fly not because of one isolated reason, but because several physical processes operate together in harmony. Air pressure changes around the wing create force differences. The wing pushes air downward, changing its momentum. Forward speed increases the amount of air interacting with the wing each second. And the shape of the wing guides airflow into patterns that sustain lift while minimizing drag. And when all these elements combine, the result is enough upward force to balance the aircraft's weight. And the myth that nobody really knows why airplanes fly comes from the confusion created by oversimplified explanations that seem incomplete when examined closely. But the deeper truth is that scientists and engineers do understand flight in great detail, even if that understanding cannot be reduced to one clean sentence without losing accuracy. And the ongoing debates are often about which explanation is most useful for teaching, not about whether the core physics is known. And as aircraft continue to evolve with new materials and wing designs, the study of airflow continues as well, refining models, improving efficiency, and revealing more about the subtle behavior of moving air. And this layered understanding shows that flight is neither a mystery nor a miracle, but a carefully balanced interaction of forces that becomes clear only when we accept that simple stories can guide us at first. Yet the full picture is always richer and more intricate than it appears. Airplanes should not be able to fly, a machine made of metal, weighing hundreds of tons, filled with fuel, cargo, and people, rising into the sky against gravity. By instinct alone, it feels wrong, it feels impossible, and yet, every single day, thousands of these giants lift off the ground and cross oceans as if the sky was built to carry them. But they do, not because gravity takes a break, not because engineers discovered a secret loophole in nature, and not because of one simple law written in a textbook. They fly because air is not empty, because pressure changes, because wings bend the path of wind, because motion creates force, because physics is deeper than we like to admit. The real story of flight is not a single sentence about fast air and low pressure. It is layers of forces working together at the same time: pressure differences, downward momentum, circulation, speed, shape, balance. It is a system, not a slogan. And maybe that is the most powerful part of this story. We often want simple answers, one clean explanation, one clear reason, but the universe does not always work that way. Sometimes the truth is bigger than the summary. Sometimes the real answer is built from many smaller answers, all moving together, just like the air around a wing. The next time you see an airplane climbing into the sky, remember this: it is not defying physics, it is using it completely. Every invisible swirl of air, every tiny pressure shift, every law of motion working at once. Airplanes should not be able to fly, but they do, and they do because the world is more detailed, more precise, and more beautiful than the short version of the story. Sometimes the world works, even when the explanation is more complicated than the story. If you enjoyed diving deeper into ideas like this, make sure you subscribe to the channel so you never miss what we uncover next. Like this video if it changed the way you see the sky, and share it with someone who has ever looked at a plane and wondered how it stays up there. We have many more journeys ahead,